In this video, we will talk about how to use a particle responses in the detector systems for the particle type identification. The goal of the particle identification is to identify a type of a particle associated with a track using responses from different detector systems. There are 5 particle types: electron, proton, kaon, pion, and muon. And there are 5 different detector systems: tracking system, ring image Cherenkov detector, electromagnetic calorimeter and hadron calorimeter, and finally muon chambers. The particle identification problem can be considered as multi-classification problem in machine learning. A particle track responses in the detector systems are used as inputs of a classifier. For an example, tracking systems provide information about particle track parameters, track fit quality, particle momentum and charge, and also decay vertex coordinates. Each detector gives a particle emission angle or delta log likelihood for different particle type hypotheses or quality of circles fit in the detector. Calorimeters measure particle energy and number of responses for this particle, for an example. Muon system tells if the track has hits inside the system or not, and how much active chambers correspond to the track. And there are many other features. Outputs of the classifier are 6 labels. 5 of them correspond to 5 different particle types: muon, kaon, pion, proton, and electron. And the last one corresponds to all other particle types and just noisy tracks that are called ghosts. Ghost is a track that was recognized by mistake or the track pattern recognition method and doesn't correspond to any real particle in the detector. So, for each track recognized in the detector, the classifier gives probabilities to belong to each of these particle types. This problem can be solved in different modes. In the multi-classification mode, in one particle versus rest particles mode, or in one particle versus one particle mode. For an example, one particle versus rest mode means that you train a classifier to separate one particle from all other particles. Modern detectors in high-energy physics provide high quality of particle identification. In terms of the area under the ROC curve, it corresponds to values in range from 0.9 to 0.995, depending on the particle type. In your programming assignment for this week, you will be able to train your own classifier for the particle identification using toy Monte Carlo sample. And you will estimate the quality of the identification for each particle type. In the machine learning community, ROC curves is plotted as a dependence of the true positive rate from the false positive rate. However, in the high-energy physics, ROC curve is plotted as a dependence of the 1 minus false positive rate from true positive rate. 1 minus false positive rate is called background rejection, and true positive rate is called signal efficiency. Quality of the particle identification depends on particle parameters such as its momentum, transverse momentum, or energy. The figure on the slide demonstrates strong dependency of the area under the ROC curve for a particle type separated from all other types from the particle momentum. The quality significantly drops in low and high momentum regions. Moreover, it's preferable to have no such dependencies. In other words, we would like to have flat or uniform dependency of the particle identification quality on the different particle parameters. Consider one more example. Consider a classifier that separates one particle type as a signal versus the rest particle types as background. output of this classifier is shown at the bottom of the slide. Let's select the classifier output threshold value that corresponds to the 60% of the global signal efficiency. It means that this threshold selects 60% of all signal particles in a sample. However, in different particle transverse momentum regions, the signal efficiency differs from the global one, as it's demonstrated in the top figure. In several regions, the efficiency is higher than 60%. But also there are a lot of regions where the signal efficiency is much lower than 60%. Such effects bring systematic uncertainties to physics analysis. And it's preferable when a classifier selects the same ratio of signal particles on each momentum or transverse momentum regions, for example. Similar dependencies are present in the modern high-energy physics experiments. For an example, the figure shown on the slide is provided by the LHCb experiment. The figure demonstrates dependencies of the pion efficiency from its transverse momentum for two different classifiers and for three different global efficiencies: 60%, 80%, and 90%. In the next video, we will consider several approaches how to train a classifier to avoid such dependencies.